Wow, I hope this is worth the wait. You've been on tenterhooks for the last 5 minutes. So, hello everybody. I want to tell you about memory allocators today. So think about C programming, a bit more low level from this morning, and malloc and free. And then I want to talk to you about a new processor technology called CHERI, which is going to enable more secure memory in our runtimes. To be precise, what we're going to do is say, hey, ChatGPT, synthesize me a secure memory allocator. And it will come back with some arbitrary C code, and then we're going to verify that the arbitrary C code generated by our AI does actually do what we want it to, in terms of respecting the malloc API. So, here are our learning outcomes. It's nearly the start of undergraduate semester, and I've been writing loads of learning outcomes for the last few weeks. Lecturers amongst us will sympathise. So here are my learning outcomes for today. So we want to, this is all Bloom's taxonomy here, appreciate why we need memory security, and look at how CHERI does memory security. That's part one. Then we want to look at how we can synthesize code to do memory allocation, and then how we're going to verify those synthesized malloc candidates to make sure they do actually run malloc as we expect them to. So the first half of the talk, probably slightly less than half the time, is looking in general about memory security and hardware and this concept of CHERI. And then the second half of the talk, which is probably where we're going to spend more time and hopefully will be of more interest to verified and trustworthy software systems people, we're going to think about formal verification once we've synthesized our memory allocators. So here are my rules of engagement. Interrupt me whenever you like. Or don't. And you can shout and wave and grab my attention if you need to interrupt me. Apparently this morning was very interactive. I wasn't here this morning, I was on the train, but this morning was very interactive. Keep it up. You're probably feeling a little bit sleepy and having a post-lunch slump, but please do wake up and interrupt me whenever you want. And I'm going to do a couple of live demos, and if, as some of you do, you have your laptops in front of you, then please feel free to get involved and follow along with the live demos as far as you can with the software you have. For the first live demo, you just need a web browser. For the second one, you might need something else, but we'll see how we get on. Okay, so let's start off with this general introduction to memory security and CHERI. Okay, so here's my first assertion. Security drives computing innovation. And I have two pieces of evidence here. One is Exhibit A for Alan. There he is there, Alan Turing. And, you know, really the period during and immediately after World War II was a time of great electronic and computing innovation, particularly because of the security needs of well, Great Britain at the time for you know, compute power and code breaking potential. More recently, that's meant to be the internet over there, you know, the threat of nuclear warfare and the need for resilient compute infrastructure led to, you know, internet protocols and things like that. And again, there were kind of security concerns that drove ARPANET originally. Okay, and I'm saying that the modern concerns of, you know, kind of threats to cyber infrastructure drive CHERI as a new compute innovation. So does this ever happen to you? Right, your university IT services, or whatever they're called in your university, send you an email saying, beware of dodgy emails and don't click on any links. And then it says, click here to find out more. Well, they say things like this, you're only one click away from being hacked. If you're kind of familiar with low-level systems infrastructure, then you know that actually you're really only one branch instruction away from being hacked. So the point is that your code can be somehow hijacked and sent in directions that you weren't anticipating or intending it to go in if the hacker can somehow inject data which possibly turns into code, or underneath into addresses that lead to code that can then kind of somehow hijack the execution flow of your programs. So here is a high-level example. This is Python. So, generally, undergraduate students adopt what my friend David Chisnell calls the vacuum cleaner model of software development. And the idea is you just go and hoover up loads of libraries from the internet and then import them and then do whatever you want. So here we've hoovered up the dodgy library. And we don't bother about looking at the API docs, and we don't bother about reading the source code. No, we just import it and say, I think I'll call the dodgy call here, and it will do whatever clever thing the documentation says it's supposed to do, or the Stack Overflow post says it's supposed to do, or ChatGPT claims it's supposed to do. So what's actually happening here? This is Python here, so we've got a byte array with 3 bytes, another one with 12 bytes, and here this is, we're poking bytes in here to say oh, and null terminating our string, and here we're saying hello, and null terminating our string, and then we print f the first string, which should say oh, and then we call our dodgy library call, and well, we're passing it tiny1, which is our first buffer, and then we print tiny2, and on our system, I want me to demonstrate this, I think. I might be able to do this, possibly. Yes, I think so. Oh no, oh, help, maybe not. Let's see if I can do something clever here. Do you know what's happened? I think I've just quit my Zoom connection, hasn't it? Has it? Oh, it has. How annoying. Right, that could be the end of live demos. Oh dear. Sorry. Right, okay, no more live demos. How annoying. Do I need a meeting passcode, Jess? Oh no, I need to use your link, don't I? That's what I need to do. Yes. Excuse our incompetence, everybody. We'll be back in a minute. Right, okay, there's the link there. That one. How annoying. About to join the meeting. How exciting. Don't want to capture audio, but I do want to share my screen. Share. That one. Share. Okay, good. How annoying. How annoying. Oh no, it really did kill it, didn't it? Right, sorry. I worry about my live demos now. Oh well, never mind. Okay, so what happens when we run this code is, here we go, run it, and it says, oh, hack! Because the dodgy call has actually somehow overwritten the memory where the hello string was located, even though the dodgy call didn't actually have a reference to the address of the tiny2 string. Somehow, with its reference to tiny1, it can reach into tiny2 and overwrite that. And if you think about this is really problematic, because you might not just be overwriting string data. In Python, you might be overwriting the actual bytecode instructions that represent your function code. If you knew what to write, where to write it, and then you'd find that your program has been hijacked, perhaps. This is what dodgy does. Let's see. So we're getting the address of x, which was our first string, and then we turn it into a very long byte array that's 2,000 elements long, and then we look through this byte array, iterating over it until we find the characters HE, or is that EL for hello, and then when we get to them, we poke some new byte to say hack, exclamation mark, and then we print it out, and we get the hack. But if we run this same code on a memory-safe architecture where, arrays and buffers are neatly bounded, we can't run off the end of an array into another array, then you get some kind of exception which secures your memory and means that you can't access things you weren't supposed to. That's good. But sadly, that really is the exception rather than the rule. So this is the world in which we live. This is the status quo. Okay, so we use word length pointers, which are really just bit patterns, to index into a large global array, which is memory starting at 0 and ending at 4 bazillion, or a lot more if you're in a 64-bit address space. And, you know, effectively, pointers are just integers. And integers could magically turn into pointers if we wanted them to. Any access permissions are enforced by the operating system, and the programming language, and specifically the program underneath, is oblivious of page tables and operating system protection bits and so on. And as far as C is concerned, all of memory is fair game. You can access it. Well, it might be undefined behavior, but more often than not, you can access some of it in interesting ways that you might take advantage of for nefarious purposes. So I was just trawling GitHub this morning, actually looking for something else, and I came across this amusing comment from a Git repository from Microsoft. And it said, who told them ints and pointers were interchangeable? And that's a problem. You can cast your, you know, int into a void star, and then indirect through it, and you've just got a handle to any piece of memory you want. How terrible. Large software corporations consistently quote that 70% of CVE's critical security bugs are caused by memory safety problems. Microsoft say that from their security response center. Google say that about their Chrome web browser with my nearly invisible URL, sorry about that. And you know, memory safety is a big problem, a big loophole that is being exploited by lots of hackers. So this is the world in which CHERI comes along and says, I can sort out the problems. CHERI is an acronym. It stands for Capability Hardware Enhanced Risk Instructions. And basically, if you think about a processor, CHERI is a kind of bolt-on to a standard processor to give you extra memory-safe features. So the data bus and the address bus change slightly, and your register layout changes slightly, and so too does the way you access memory. But, you know, if you squint, it just looks like a normal RISC processor, like ARM or MIPS or RISC-V or whatever. The project that started this is pronounced custard. So I think they've got their T and S the wrong way around for custody, but custard it is. And custard is from Cambridge, and Professor Robert Watson there is really the main instigator. But since then, it's kind of blossomed, ballooned perhaps, and lots of UK-based universities doing research into custard, or more precisely, CHERI, one of which is Glasgow University, where I'm based. So the thing to think about really is the capability. The capability is the way you access memory correctly. So a capability, formally, is an unforgeable token of authority that gives you the right to do something in a particular context. But let's kind of forget about formalism for a minute and think about a kind of ridiculous analogy, because analogies do help us to understand things. So, imagine you want to go to a Taylor Swift concert, or something like that, okay? Here's your ticket. Can you see that back there? It's a bit dark, isn't it? That says access all areas. And that means you can go anywhere you like. Access all areas. You have the permission to go anywhere and do anything. That's like a C pointer. Access all areas. You can go anywhere you like in memory. Okay. Here is a ticket with a specific spatial constraint. Admit one person, and that one person must sit in row 4, seat 2. Congratulations, there you are there, row 4, seat 2, excellent, good. So that's a spatial constraint. You see, that ticket only admits one person to one particular place. You can have a temporal constraint as well. Admit one. 13th of August, 2024. Ha, I modified it, especially for today. Good. So that one person can go in today, but the ticket is entirely useless tomorrow. A temporal constraint. And then you have, here's a train ticket. It's an old train ticket. But if we travel back in time to the 18th of May, 2022, then in possession of this ticket, you could have gone from London to Glasgow on B25F seat. You couldn't have sat anywhere else. And Virgin trains, or whatever they're called these days, are very, strict about where you sit on your trains and whether you're on the right time train and in the right place. They do enforce temporal and spatial constraints very carefully. So this ticket here has both temporal and spatial constraints, and that's the point of the capability. If the pointer just says, you can go anywhere and do anything, trample all over memory, do what you like, the capability says, you are only allowed to access this specific subset of memory at this specific interval of time. So the capability is like a kind of time and space constrained pointer, and that's the key thing to take away from CHERI. So here is a 64-bit pointer. Here is a 129-bit capability. So you've still got your pointer, which is your raw integer address, okay, which is going to index into memory, but now you also have a base that says, thou shalt not go below this address, or your pointer becomes invalid, and a limit, which says, thou shalt not go above this limit, or your pointer becomes invalid. And then some metadata that says things like, you're allowed to read through this capability, you're allowed to write through this capability, you're allowed to execute through this capability, you're allowed to update capabilities through this capability, and there's several bits of metadata. And then there's the tag, and the tag is this extra 1 bit. So this here is 128 bits, 64 bits for the pointer, and the base and the limit and the metadata are compressed into a further 64 bits, that's 128 bits, which lives in memory directly, and the tag is kind of stored off to the side somewhere, and the tag is a single bit that says whether this capability is valid and can be used, 1, or invalid and cannot be used, 0. And once your tag bit's been cleared, the capability becomes invalid and it can never be valid again. Ooh. So unless it's blessed by another valid capability, but once you lose your validity, you can't reacquire it by yourself. So there's kind of monotonicity here. You can go from valid to invalid, but you can't go back to valid again. So, capability semantics. All memory accesses are checked. They're provisioned or resourced through these capabilities, and capabilities are checked dynamically in hardware. Is my capability valid? Is that validity tag set to 1? Is the reference inbound? Is my pointer above my base and below my limit? Possibly less than or equal to? Yes, okay. And is the action permitted? Am I allowed to read or write or do whatever I'm trying to do with this capability? If so, that's fine. Memory access occurs as normal. But if not, if any of these checks fail, then the processor raises an exception. And has anyone ever had a segmentation fault in their C program? Seg fault, yeah. So the seg fault generally is kind of access to another pointer or something like that. Okay. So you get these specific faults here, a bit like a seg fault called a protection fault, which means you tried to do something with a capability, but you weren't actually allowed to do that thing. So this is the new violation, and that can be handled with interrupt handlers and so on at runtime. Okay. Now, do you remember I said with a pointer you can access all areas and you can kind of cast an integer to a pointer? That's not true for capabilities. So capabilities, you somehow receive a capability from someone who has it, and once you've got it, you look after it, and you can kind of use the subset of that capability's permissions, but you can't somehow grow your permissions or your memory bounds in any sense. So capability can be inherited from a parent context, or received by the operating system, called malloc or something like that, or derived from the existing capability that you have access to, like the stack pointer, say. So you can offset into the stack. But you can't, magic up, forge, construct a capability from a bit pattern, because it will always have that 0 validity tag, which you can't turn into 1. There is real hardware that does this. A processor from ARM called the Morello, and there it is there in all its silicon glory, and an FPGA board called CHERI Sonata, which is a RISC-V board there. And oh, how exciting, we have a question. I'm going to take an interrupt. Congratulations, first inquisitor of the afternoon.
Is there any reason you're focusing on hardware changes rather than like software changes, like you mentioned casting between integers and pointers? If we just forbid that, then presumably it's kind of capability safe like construction.
Okay, so if your tool chain that you're using is somehow safe, and doesn't allow you to do these dodgy things, then you can be sure that the code you generate is safe. Okay? But if that code is ever subject to external influences, rely on C library, say, or you dynamically link against something, or you receive input from a user that could possibly not be checked properly, then all bets are off.
Yeah.
It's a bit like Rust. You know, you use Rust, you say, but anyone here a Rust station? Wow, how exciting, yeah. You use Rust, you say, everything's great, and then you say, how do you say, unsafe, okay, packets, and all bets are off.
Yeah.
So I think this is kind of belt and process protection, even for those common cases.
Yeah, I mean, there's an interesting trade-off though, because I mean, if you say like let's create a language that's like exactly the same as C, you can't pass between a pointer and an integer. Okay, now all your libraries are going to have to go back and change those. So there's a big cost to
You're right.
Like,
the legacy code base problem is
but there's a big cost here too, because you're going to have to get the hardware and run it on that hardware, right?
Yeah.
And it's safe if you use this hardware, and then that's kind of analogous to it's safe if you use a single library. Like not everyone has the hardware in the same way. Not everyone's using verified libraries.
You're right. So there are 100 of these boards around, 2 on my desk, and there are 1,000 of these machines around. 3 on my desk. Oh, no. But you know, these are kind of rare things here. Yes, yes. So the hope is they will become more and more prevalent. And if you look at companies like ARM and Intel and Oracle, they are incorporating not exactly CHERI, but some kind of memory safe features into new generations of their chipsets. Tags to indicate kind of pointer permissions and things like that. So there is certainly scope for some of these in new generations of hardware. Yeah. What's the answer to your question? I think it is the world is complicated place. I think that's the answer. Yes, good. Oh, another question. Hello.
This is going back a bit, but when I first started work, I started working on this machine.
Oh, how
it
nice.
had tagged architecture.
Is this in the 1970s?
Yeah, this is something late 80s.
80s, okay.
But yeah, it had tagged architecture, so it had all this stuff. So why the gap between then and now?
Yeah, why did we give up on it? So I think, as we'll see later, there is an overhead to pay for this tagging, this runtime tagging. The overhead is non-negligible, but I think it's small enough that you could justify it now, given the security concerns. And indeed, if you look at, still just about hanging on, US President Joe Biden's recent White House report on computer security, he mentions CHERI and says, I can't do a Joe Biden accent, he says, we need CHERI. So that's very, very interesting, isn't it? So even, the great and the good, if Joe Biden is great and good, are thinking about, memory safety and looking at technologies like this and possibly wanting to encourage their adoption in the US military and places like that. Yes, okay. Yeah, thank you, that's a good point. So tagging is not a new idea. Capabilities aren't a new idea. The original capability machine was in the, 60s, 70s? Yeah, long time ago. Yes, good. Okay. Oh, hello!
You showed a picture of FPGA, so I was wondering what it is doing and in what way it implements memory safety.
Oh, right, okay. So there's a model of a RISC-V core which is implemented in System Verilog that includes all these kind of CHERI features that then kind of flash onto the FPGA. So it's a RISC-V soft core in an FPGA. Yeah. So Google Sonata CHERI RISC-V, and you find out all about it. And you can get the FPGA model that you can stick on some kind of FPGA board from Xilinx, I think. Yes. Good. Now, this is really nice, and thank you for those 3 interruptions. That's fantastic. I'm going to have to speed up a little bit because we have more exciting stuff to talk about. So, the UK government has sunk lots of money into CHERI to the tune of 100 million quid, some of which came to us at Glasgow, yay! And some of which went to ARM to persuade them to build lots of these boards, and all the money's run out now. How sad. Right, so live coding example. Now, this could crash my Zoom again. I wonder if I could do something really clever to avoid crashing Zoom. Possibly not. Right, I'll tell you what we'll do. We will do it anyway. Okay, let's kill Zoom. Right, okay. So, I'm going to press escape. And, oh, Zoom didn't crash. That's very good. That's very good. Excellent. Right, okay, good. So, if you have a browser in front of you, can you navigate to this website? capabilitiesforcoders.com/Cloud Shell. Does that work? Cloud Shell. Can you see it there? capabilitiesforcoders.com/cloudshell.html. Now, if you all do this, it'll go very slowly because this is really some poor Docker container sitting on a virtual private server somewhere. But hopefully, it might work. Maybe? No, maybe not. Let's think about it. I'll leave it there for a minute to think about. So if this, oh yes, how exciting! It's come alive. Good. So look, here we have, I'll make it nice and big for you. Here we have a software emulation of a CHERI machine. So if I say, I wonder if I can say uname on here. Does that work? Oh, it's very slow, isn't it? Yes, here we go. So this is running FreeBSD, and it's running on a CHERI compatible system. Let's see if this works. Here we go, CHERI BSD running on some kind of, here we go, ARM64 capability server. There we go, ARch64C. So this is an emulated CHERI machine here. Now, what we want to do is to try and run some C code and run it on a kind of normal system and see how we can trample all over memory, and then run it on a nice capability system that has these hardware bounds checks and see that it's not going to work. So I wonder if I can find some code here. Yes, maybe. Right, here's some C code. What's it doing? Let me see if I can make this a bit easier to read. Can I? That better? No, maybe not. Oh dear. Right, so in our C code here, we've got two strings. One's called password and one's called user. And we copy some data into the password, it's secret. And we copy some data into the user, Jeremy. And then, look at this, we start at the beginning of user and we dump out character by character all the characters of the user. Oh, but we don't stop, we carry on. And we carry on past the end of user, so we're going to print out the secret as well. So if I run this code, let me just kill that there. If I run this code now, we should be able to see the program printing out the user string and also the password string. Let's see if I can do that. Clang bounds.c. So this is just running on my MacBook here. And if I say a.out, good, right, so it prints out Jeremy, and then it prints out some whatever null characters, and then it prints out secret, and it prints out some more, and it prints out those 30 characters, those 30 bytes from the stack, which I asked it to do. And it was very happy to do that. But of course, really, I only had a handle on the user string, which was only 10 bytes long, so I shouldn't have been able to look at all the other strings as well. I shouldn't have been able to access them. This is the same problem with our oh hello thing that we saw before. So let's try and run this same program here, bounds.c. Let's try and run this program on a CHERI machine now and see what happens. So I'm just going to take my bounds.c, open, find a dot. There it's there, bounds.c, and I'm just going to drag and drop this onto my CHERI Cloud Shell, bounds.c, and it's uploading it to the Docker instance. Bounds.c was uploaded to your home directory, so it's there, I hope. Let's see. Is it? Vim, bounds.c. Bounds.c. Yeah, look, there it is there, exactly the same program. Okay, I've still got that commented out down the bottom. And now I'm going to try and compile it here. So let me get this right, Clang Morello. march equals Morello, that's the special ARM processor variant. ABI equals pure cap to say I want to turn on the capability extensions, bounds.c, and now when I run it, hopefully it should crash, which is good because it's trying to access something I shouldn't have accessed. Taking a very long time to compile. A.out. Oh dear. And it now should take a long time to crash. Good, look, in address space security exception. So what's happened is I've tried to access data through a pointer, through a capability I wasn't allowed to access, and the system falls over. Great, we are very happy. Back to PowerPoint. Okay, so if you want to, you can go to this Cloud Shell thing, capabilitycode.com/Cloud Shell, and you can play around with capability extensions, and you just need to use these flags here to say you want to use the Morello ARM processor backend, and you want to use the pure capability architecture binary interface. Okay, great. Right, that's the end of part one of the talk, introducing memory safety, kind of motivating why we want hardware security extensions, and talking a little bit about CHERI as one of these possible technologies that give us hardware security. So I'm going to pause for a minute and catch my breath and allow interruptions. And one is queued up waiting for me already. Hello.
Do you have the same problem with reading data loss versus being able to read on the heap?
Yeah.
What I'm thinking now
Good.
is so the problem is so you're able to read from the password handle via the user handle.
Yes.
But because these are both on the stack, you have access to the password handle anyway. So
yes, via the stack pointer. Yeah. Okay. Well, it would be more of a problem perhaps if I had passed, as I did in my Python example originally, passed the user handle to another function in another context that then read from the stack frame that it wasn't supposed to, perhaps. But yes, this does translate perfectly to the heap context, where you're dynamically allocating memory and you only want to access the portion of the heap that you mallocked and not be able to go beyond that to look at other client code malloc calls. Yeah, thanks. That's very good. Yeah. Any more questions or comments about CHERI or memory security? Hello. Yes, my list friend.
You might already talked about this. You said malloc was an operating system.
Oh, sorry. So really, Mmap is the operating system API, and malloc is a layer on top of Mmap. Yes.
Which tends to be a user space.
Yes. It's in a C library. Yes, that's right. Yeah. But when you call malloc, underneath the C library is doing a system call to get a large buffer of memory, and that large buffer of memory, which is managed internally by the C library, will come with an operating system capability that can address the whole of it, and then malloc will give the user application back a more constrained, kind of more tightly bounded capability, a narrowed capability, if you like, that can only access the portion of the heap that is meant.
Not made malloc to compromise its own data.
Yeah, so you need to, as the library implementer, protect that kind of more privileged capability. Yes, that's correct. And we'll look at some malloc implementations later and see how that might work. Thanks, that's a good point. Yeah, hello.
When you support the bit capability.
Yeah, the 129 bits.
Yes.
Yeah.
There was a base and top of it, and then there was a pointer in the middle.
Yeah.
So the base in the top part would indicate the range that you can
Yeah.
access.
Yeah.
So then the pointer in the middle is indicating, I'm assuming that would be the part that you're trying to perform the action on.
Yeah.
So then, is that determined by you, but then the base and the top shouldn't be determined by you, because you're not supposed to say what you're able to access, right?
Yeah. So the base and the limit indicate the sort of valid range, but that pointer can go out of range. So just in a normal C program, you can take any pointer you like and say, add 1,000,000 to it, And if it goes out of range, well, that's still valid C. You can still make the pointer go out of range. You just shouldn't dereference it once it is out of range. So the pointer itself is just those 64 bits that can be taken out of range, but then when you try to dereference it, you check those 64 bits against the base and the limits to see whether it is out of range or not.
So it's the operating system that generates that capability set of bits?
It's the processor hardware,
Right.
yeah, and the operating system will manage that, but the actual bits are generated in the hardware, yes. So your register file now has 129-bit registers to store these values, and your memory has 128 bits, 16-byte aligned addresses in it, and then these kind of extra tag bits live in kind of side bit vectors in the edge of your memory. Yeah, thanks, that's good. Yeah, okay, great. Just a quick question. Give me a wave. Has anybody kind of played with CHERI before? Are there any experts amongst us? Ah, well done, yes. Oh, good, okay, great.
One of my colleagues is doing his thesis on sandbox.
Oh, yeah.
CHERI is an example.
Good, okay.
Sandboxing, you got a sort of programming experiment.
Very nice. Yeah.
Difficult it was for a programmer to understand what you needed to do to change a C program.
Yeah, sure,
so he was
sure.
looking at the usability of the changes.
Okay. Well, that's very interesting.
Option of the CHERI.
If you're going on the walk later on, I'm going to walk next to you and have a talk about that. Thank you, that's very nice. Oh, you're not? Oh dear, well, never mind. Okay, I'll stalk you some other way. Good. Right, here we go. So we're moving on to the second part of the talk now, and just on time, we want to think about memory allocation. So this is low-level C memory allocation. You call malloc. You get back a buffer which you can access and read and write, and then eventually hand back to the C library when you call free. And this is manual memory management used in C and C++ and similar kind of low-level imperative languages. So the place we started was with the Capable VMs project, which was run by myself and Laurie Trapp from King's College London, with colleagues from ARM and kindly bankrolled by the EPSRC. And in the Capable VMs project, we looked at virtual machines and kind of Java, Python virtual machines and so on, and thought about how we could use capabilities to make these VMs more secure. And one of the things we did a couple of years ago now, 1 year ago, was look at malloc implementations which find their way into low-level systems code like virtual machines, and see whether these allocators have been properly adapted for capabilities for CHERI. So, like you were saying, earlier, how do you modify the legacy C code to make it somehow capability aware and to give it the advantages of the security this capability model provides? So, what's this saying here? For a trivial bump allocator, which has 61 lines of code, you need to change 50% of those lines in order to make it capability aware. But that's really a corner case. For a meaningful allocator like JE-malloc or SN-malloc, which are kind of industrial strength allocators, you're changing perhaps, 1 to 2% of the lines of code in your allocator. So 1 line in every 100 needs to change for this low-level systems code. Possibly it's typecasting, possibly it's kind of capability metadata management, but you need to change some proportion of your code in order to make it CHERI aware, CHERI compatible. Okay. Now, CHERI is not just kind of, security fairy dust. You can't just kind of sprinkle CHERI on top of your C code base and say, it's secure now. And we demonstrated that because it's still possible to somehow violate some security concerns, to kind of do things to circumvent some of the capabilities. And the paper we wrote last year shows some of these things. Even in capability aware allocators, you can still access memory you shouldn't perhaps. Yeah, now, here are some benchmarks, and really the only figure to look at, the only bar to look at is the kind of steely grey one on the left to reach, because that's the execution time, normalized execution time. And if you look at capability code versus legacy pointer code, there is always an overhead with the capability. You'll see there's 100% overhead. Oh dear. There's maybe a 50% overhead. So you see there's a high overhead here. These overheads have come down, and now you're talking about a price perhaps a 10% overhead for having capabilities as opposed to just using raw pointers. And this could be reduced even further with more hardware optimizations. But what these things here are showing for these benchmarks, okay, and for this particular allocator, I think this is the JE malloc implementation here, what we're showing is that you can take a legacy C library memory allocator and somehow modify small portions of the code base to make it CHERI compatible. So what if you said, let's start on a greenfield site. Let's start with a blank slate. Let's create our own custom memory allocator that's just for a CHERI architecture. We won't be constrained by the design decisions of 1980s systems programmers who wrote their memory allocators a long time ago. No, we will create a new custom memory allocator that's just for CHERI. Okay. And this is our new project, kindly funded by VeTSS, or at least UKRI through VeTSS. So thank you very much, Brijesh and Azalia and everybody else. Yes, this project is with Glasgow and Leeds University, and it's making memory more secure. And the next few slides come from Zheng. I think the next 2 or 3 slides come from Zheng, so I'm indebted to him. So this is what I was saying before. Loads of vendors like Oracle and Intel and ARM are adding tags and kind of extra features to their processors to make them more secure in some sense, to improve the security of pointers. And loads of software has custom allocators, and we want to somehow create new custom allocators for CHERI. So what we do is, instead of actually creating a custom allocator, we're just going to use machine learning to synthesize a new allocator. ChatGPT, give me some malloc code. So we don't actually do that. We say, PhD students, give me some malloc code. And then we kind of run it through some kind of convolutional network or something. Anyway, once we get our code out, right, then we want to verify that this code really is a good malloc. It does actually conform to the malloc specification, so we use some model checking based on the kind of properties we understand about how malloc works to try and verify that this is a good piece of code. So there we go. Write me a secure C memory allocator with bounds checking. Ooh, here's what ChatGPT says. You can't quite read it, can you? It's not a very good allocator, but never mind. Okay. But there are lots of more sophisticated ways to generate malloc candidate implementations. So now I'm going to crowdsource the next slide. How would I synthesize a memory allocator in C? What do you think, dear audience? You can't say ChatGPT because I've got that one already, and that's a first year undergraduate answer. What would you do to synthesize some code? Ah, Brijesh, what would you do?
I have no idea where to start.
No, okay. Anyone else help us out? How do we synthesize? How do you synthesize code? Oh, a step. That'd be good. Yeah, we have a step. Yeah, okay. Then we somehow lower the specification to code, and there are ways to do that. Yeah, certainly. Okay, good. Yeah. Anything else? Anything more adventurous? What could we do?
Do you not need some sort of structural model of what it is you're trying to generate?
Ah, good. So we are using the structural model for the verification rather than the generation. So, yeah, but I suppose, yeah, we could have done it that way as well. Yeah. Come on, crowd. Anything else? Oh, hello!
Brute force.
Brute force, very good. Okay, so you have your kind of million monkeys with your million typewriters, and you get the complete works of Shakespeare, yes, eventually. Yeah, okay, that's good. Yeah, thank you. Good. Yeah, any more suggestions? I'll tell you what I put. Okay, so I said we could have, what did I say? Oh, genetic programming. So we could take some existing memory allocators and we could somehow munge them together with some kind of genetic programming system to create new memory allocators. We could do some optimization, which is brute force, effectively, where you kind of iterate through sequences of instructions and try and generate kind of sequences that do new things. We could do some kind of deep neural network machine learning to generate code. Yeah, but all these things are going to generate code that we're not really sure what it does. And, this isn't ETS, this is VeTSS. We want to verify our software systems. So how do we ensure that these kind of synthesized, generated codes are correct? Now, we wouldn't have had the problem with your suggestion synthesizing from a spec, because that would, so long as our synthesis procedure was kind of formally specified and verified to be correct, that wouldn't have this problem. We'd know that our candidate solutions were okay. But if we're just kind of generating arbitrary code, how do we ensure that it's doing the right thing? Well, you know, go and ask a random software engineer, and they say, oh, you need to do fuzz testing, or you should have a, you know, conformance test suite with high coverage, or you should use Valgrind and do dynamic instrumentation to check that your behavior is correct. But really, none of these are very kind of sound techniques. So really, we need to think about the semantics of malloc and how it works, and then try to somehow specify these properties, and then verify that our candidate implementations do match these properties here. So there have been attempts to formally specify the behavior of memory allocators, and I just picked out some of the literature here. Most of this is fairly recent literature within the last 4 to 5 years, perhaps. Okay, so this is from Oxford University, published at TACUS a couple of years ago, I think. And this is looking at, again, particularly CHERI and the kind of semantics of CHERI C, including allocation. Okay, what that looks like. Here's a very nice paper from Andrew Appel, published 3 or 4 years ago, that's looking at a kind of single-threaded implementation of malloc and verifying that it does what you expect it to. So they take some kind of simple allocation library and show that it does conform to the expectations of a memory allocator. And then there's also this Cerberus C semantics specification here, which again deals, well, with the whole of C, in fact. This is from Peter Sewell's group in Cambridge, and they have a page or two talking about malloc and what you expect malloc to look like and how it ought to work. So there are kind of formal specifications for what malloc ought to do, and they probably look something a little bit like my things here. So it returns a valid buffer or null if there's no space. This buffer isn't reallocated before it's freed, and you need to be able to pair up every malloc with a free, and you don't want to free things more than once, and you mustn't forget to free things. So these are kind of, I suppose, user level expectations on the malloc implementation. And here they are neatly formalized. So, oh, hello. Hello.
Some of those were more about how the user should use malloc.
You're right. You're right. Good, good, good. So I think I said here, yes, look, these are malloc semantics from the perspective of the client. So it's almost like the interaction between the client and the allocator. And I think this is what I was scribbling down here from that perspective. But these formal semantics here are actually the semantics of the malloc itself, I think, rather than the malloc client interaction. Yeah, so that's a good point. Thank you. Thank you. Yeah. No, let's just go back to this. Let's see. I think, yeah, all of these things are kind of viewed from the client's perspective. I suppose the first two are probably internal properties of malloc, aren't they? And these are more kind of properties of the client. So 3 to 6 are properties of a well-behaved malloc client, and 1 and 2 are properties of well-behaved malloc implementation, perhaps. Now, I'm not claiming that these are exhaustive. I just kind of scribbled these down on the train this morning, oh no. But I think they certainly capture some of the expectations of a malloc implementation. Okay. Oh, hello.
So I mean, this is very specific about malloc. But
It is.
Suppose you are just a quote-unquote user, or you learn about C or C++ and think naively, or let's say textbook style, like you follow the tutorials, or let's say you just try to get things done.
Yeah.
And assume that malloc has been designed safe by default.
Yeah.
And then you run into unexpected. So you know, there's a consortium for C and C++ that are dealing with updates, and specifically for C++, there's so many consortiums, so many updates. It's very difficult, it's amazing itself, but should it be safe by construction?
Yeah, yeah, okay.
And even Rust, so you mentioned this technical resource, even Rust has some issues.
Yeah.
Not very safe.
Yes, yes. So I think if I could try and rephrase your question and turn around and ask it back to you, you're saying, should all programming language libraries be well specified and correctly implemented?
Yeah, it's a bit like, when I board an airplane, so I sort of assume that there's a pilot and he knows what he's doing, and I assume that the engineers who built the airplane.
Thank you.
And the thing is, I cannot mess around with it anyway, right? Because if I knock at the door and say, Mr. Pilot, how are you doing? They will, let's say, escort me out, and I will get myself in trouble. So the problem is a bit, I know it's complicated and it's abstract, but then, engineering my way around malloc just because I think I'm doing something better than what's already there might make it worse.
Right, good. Sorry, I see where your question is coming from now. So I think what I'm talking about here, this synthesis of malloc code, wouldn't be something that the average programmer would do. I think this is something that a systems implementer would do. So this might be someone who is going to release a new operating system, or someone who's going to deliver a C library implementation for a new processor. So I don't think the common or garden programmer will be writing their own malloc specification. I think this would be something that would be done less frequently by specialist developers or teams of developers who are systems implementation gurus, perhaps. There's an interesting website somewhere. No, it's actually a tool, I think. Is it called Smart Count or something like that? And it kind of, you point it at a GitHub project, and it tells you if you paid your developers the kind of US average salary for developers, how much each open source project would cost. And if you do this for memory allocation implementations on GitHub, this project would have cost £2 million to develop, or something like that. So, memory allocation code is quite complicated and quite expensive to develop. And if you want to kind of roll a new allocator for a new processor with new features, then maybe you do want to kind of throw machine learning at the problem to save yourself, 10 person years of development time, perhaps. Yeah.
Well, what's the website called?
Let me see if I can find it. It's, I think it's David Wheeler. Let me see if I can find it. David Wheeler slot count. Is that the one? Yes, here we go. This is it. Good. Slot count. So, I think, is that the right one? Yes. Let me see. Is that the right one? Yes, there we go. That's the one. So if you just search for slot count, it's a command line tool, and you give it parameters and things, and you say, here's some source code, tell me how much it would have cost to develop this code, and you should back a number. Whether you believe that number or not, I don't know, but it's very interesting. And yes, we use this to justify our grant application anyway. Good. Right, so what I want to do for the last part of my talk now is show you how we're using model checking in, at the moment, a simple way to try and verify properties of candidate memory allocators. So we are using the spin model checker with linear time temporal logic, and we're trying to understand how a malloc implementation can be abstracted away to a model that you can then verify properties on. And the next few slides are courtesy of my colleague Alice in Glasgow. Okay. So if you imagine program execution as a kind of trace of states that you pass through, okay, then you can specify properties about each of those states, or about paths through the state space. Okay. So here, box P says that property P is always true in the future. So for every state in this linear trace of states. And diamond P means P is going to be true at some point in the future. It might not be true now, but it will be true eventually. Okay. So these are kind of LTL properties here, kind of universal and existentially quantified properties. Okay. Right. So what we're going to do is we're going to take some C code that implements a memory allocator, and we're going to turn it into a finite state machine, effectively. So here's an allocator which has 4 states. A question? Ah, thank you. The bell ring because you wanted to ask a question. That's very impressive. Good.
I'm curious, why did you choose the spin model checker among all others?
Yeah, okay, so you're model checking expert. I'm going to talk to you later as well. Good. So Alice is our friendly model checking person in Glasgow, and I'm not really a model checking person. So everything I say to you for the next 10 minutes is from the perspective of an enthusiastic amateur rather than a professional model checking person. So if you know more about model checking than me, please do correct all my mistakes. Hello, yes.
So maybe better before you start this complex explanation.
Hmm.
You give any kind of introductory example. You just know at the beginning from a cyber security point of view, for example, the hacker may hack your memory. So you use this type of thing to do the memory allocator or management, whatever.
Yeah,
So
yeah, good.
The thing is,
yeah.
Yeah, could you put it in the scenario, how do we approach this problem at the very beginning to set the...
Yeah, good. Okay. So we need the kind of 30,000 foot view. Right, let me think about this, Okay. Writing memory allocators is difficult. Due to a sudden explosion in diverse compute processor extensions for memory security, we're going to need a lot of new memory allocators. Oh, and we want these memory allocators to be secure, to avoid them being exploited by malicious hackers. We can't be bothered writing our own memory allocators because it's hard work, so let's just synthesize them with automated tools. But we want to be very sure that the output of those automated tools is correct in terms of the memory allocation contract, which we're specifying in some formal way. So the model checking here is just to say, here is a candidate malloc library, does it do the right thing? And the right thing in our case is that it does what you expect to see memory allocator to do, and that somehow it has additional security properties that I've glossed over and haven't specified at all here, but maybe those are enforced directly by the hardware, so I don't need to worry about them.
And to my naive understanding, for example, maybe at the hacker knows the conventional memory allocation, then it will be very easy to manipulate the memory. But if you have kind of tool, or you yourself can change the structure of the memory, so automatically the hacker cannot do the thing easily. Am I understanding why?
Oh, security by obscurity. No, I don't think so. I think we want to build in security mechanisms that prevent the kinds of exploits like buffer overflow and return-oriented programming that are very common today. And the way that we are preventing those is directly in the hardware. The instruction stream won't allow us to do these things because they're somehow abuses of the pointer model. But in order to actually have an allocator running on this specialized hardware, we need to synthesize it. Am I making any sense here? Yeah. At the moment, all we want to use the model checker for is correctness of our malloc implementation. And we're using a new malloc implementation because there isn't a good malloc implementation for this new platform that we're targeting at the moment. Does that make sense? Possibly. Thank you. Sorry. Oh, hello.
Just a quick question. What kind of guarantees can you obtain from this before we can justify going through the process of generating something automatically instead of putting in the time to create by like having humans creating the actual model?
I know. So the question is about, can we really balance the kind of risks of using automated code generation versus having expert humans generating our code for us? Even expert humans make mistakes sometimes. So it could be that when we have our nice model checking pipeline up and running, we check existing malloc implementations, see if they're actually correct in terms of our expectation of what malloc ought to look like.
So you think this is the first step to then possibly then further improve it afterwards. Is that what you meant?
Yes, I think that might be fair. Yeah, I think so. At the risk of just agreeing with you. No, I think that's probably true. I think so. Hello, another question.
How comprehensive can the specification in LTL be?
Good. Okay. So how complete are our specs? Yes, that's good. And at the moment, no, they're not complete at the moment. We're just looking for specific things. And I think we want to be informed by some of those papers that I showed before that do have full semantics from malloc and kind of somehow extract from those kind of properties we want to use. The other thing to say is, now this is where I'm going to defer to model checking experts. Model checking somehow looks at scenarios and specific cases and doesn't necessarily give you kind of cast iron guarantees for all cases. It's only for the kind of specific kind of model that you set up. Is that right? Where's the model checking expert gone? Hello, yes. So I think model checking with some confidence. You can't say that,
If you are using something like CPMC, then it takes C code as input, so you don't really need to model it anymore. It's a C check.
Yeah, okay, so we should talk about that too. So at the moment we're somehow lifting a model from our C code, and at the moment that's being done manually, but what you're suggesting is a way of somehow providing C code as input directly. Yeah.
In my PhD, I deal with like direct system build-up codes instead of actually modeling hardware.
Very nice. Okay, so yes, I want to talk to you afterwards as well. Don't go home without talking to me, please. Yes, good. Okay, that's very nice. Good. Oh, hello. Sorry, another question. Yes, please.
Just remind me why can't we just use a conventional malloc implementation and let CHERI, compile it under CHERI and let CHERI tell you when you're not doing it right? Malloc hands out pointer, you go and use it. If you misuse it, the architecture goes bang. And why do we need a specialist malloc implementation?
Yeah. Okay. So the question is, can we just port an existing allocator to CHERI and let CHERI dynamically tell us when there are security problems? So I think, I'm going to scroll back to a previous slide here. I think our paper that we published last year, which looked at some existing malloc libraries in CHERI, showed that even though these had been ported to CHERI, they still have some exploitable vulnerabilities in them. And also, there is, in some cases, quite a high runtime overhead. So we want to create a sort of CHERI-specific kind of made-to-measure malloc for the current instantiation of the CHERI architecture. And when next year the new secure Intel architecture comes out, we want to just kind of turn a handle and produce a new custom malloc that fits that neatly. So I guess that's our motivation. Thank you. Hello.
How do you find those vulnerabilities so you had it on the table?
Oh yeah, that's right. Yeah, and I don't really go into what they are. And some of them are perhaps not directly exploitable. There's things like where you allocate some memory with a huge bound, and then you reallocate and say, reallocate with bound 1, and then you still have the old pointer kind of kicking around somewhere, the old capability you can kind of access past the end of it. So those are somehow exploits that are very capability specific, and you need carefully constructed code to use them.
Are you also saying that that's not patchable? Or?
You can fix that, but these existing libraries don't. So it is patchable, yeah, but they hadn't considered that corner case when they did their CHERI, bounds porting to their legacy libraries. What am I trying to say here? Sorry, I'm getting very confused. I'm trying to say that, yes, if we started from the ground up and wrote a new allocator, then we could kind of, build CHERI in from the start rather than trying to somehow, crowbar it in afterwards and possibly miss it out in some places. Yes, but these things could be patched to make them more secure and possibly slower as well. Yes, okay. Good. Right. So what I want to do just for a few minutes now is show you these finite state machines, which are, as we said before, lifted from C code that implements an allocator. So this is like malloc here. So we receive a request, in stage zero, we receive a request for distance units of memory from user I. User I is a client of our library. Okay, so we've got our kind of memory buffer here. Okay, this is just a kind of simple bump pointer allocation. So here's kind of start here, and we say, well, have we got dist units of memory in there? And if we have, then we shall allocate those and return this pointer to our user. And then we mark the memory as not free. So we've got some kind of bitmap on the side, and that bitmap here is going to say, 1, this memory is all used, and this memory is not used. Okay, so that's our allocation process. There's another kind of side bitmap as well that says whether anything's been written to the memory and who it's been written by. So at the moment, nothing's been written here, so it's all kind of nulled out. There's nothing in there at all. Okay, so that's our allocator process. Then here we've got the reallocator process. Really, this is the garbage collector, the things that freeze memory. So we receive a request to reallocate memory from position start. So this memory is no longer going to be used. Fantastic. No longer going to be used by this client. So it's giving the memory back to the system, if you like. So we mark the units as free. Turn those all back to 0. 0, 0, 0, 0, 0. Woo! And then we set the data in that chunk back to null where it was before, and this memory is now once again available. Good. Okay, sorry, I promised I wasn't going to use the blackboard, and now I am. I do beg your pardon, Jess. Sorry. Okay, here's a user process. This is the client application. So this client application here, let's see, calls malloc to request some memory from the allocator, and then it gets the start address back of that memory. Okay, and so in this case, if the start is an error value, then we say there wasn't enough memory, so we kind of throw that away and go back to start. That's like we couldn't satisfy the request, so we return null in malloc. And here, if the start is less than the total length of memory, then we have satisfied the request. And so here we do a dynamic check of the memory content to see if there's anything in there. Hopefully it'll be nulled out, there's nothing in there. And if it's nulled out, then we write something to the memory. And when we write some data to the memory, here we go, data. We also at the same time write to this sort of ownership buffer here to say, it's my memory, I'm using it, so 1, 1, 1, 1, 1. Okay, and that should still be 1, 1, 1 there. We allocate it and set that to 1, 1, 1 there. Okay, so this says, is it free? And this says, who does it belong to? And this is actually the data that's set in. This is quite a complicated memory allocator with 2 side buffers of metadata, one to do with ownership, one to do with whether it's free or not. Possibly we don't need both of those really. and one to do with the actual data itself, which would be much bigger. Okay, well, this is the metadata here. So that's the free space, and that's the memory M-type thing there, which can either be, it belongs to process 0, data belongs to process 0, data belongs to process 1, or it's nulled out, which means it doesn't have any data and it belongs to anybody. And what Alice is trying to set up in this particular mod checking example here is to show that if the data in the buffer does belong to process 1, then process 2 should never be able to access that data. So something that belongs to 1 should never be readable by 2. That would be a kind of leakage of information. Okay. So this is a Promula specification of the allocator here. So the allocator receives a request from a process with a certain ID for a certain amount of memory, and then it somehow allocates that memory and returns the start address to the process, and then it says this space here is no longer free, it's in use, and that's the end of the allocator. So the allocator identifies a block of memory, marks it as in use, and then returns the start pointer of that memory block to the client process. And the reallocator, or the collector, gets a request to say, we no longer need the memory address start, that goes on for distance, that's the start, that's like the base and that's the bounds. So we say that it's now free, 0 it out again, and set the belonging buffer to null for that particular unit, and then we're finished with it. And now this memory is once again allocatable. So the realloc blanks out that, whether it's free or not, and that, whether there's any data in it or not. Okay, and here's a user, a client process. Oh dear, this one's a bit more complicated. What does this do? It asks for some memory. I think 2 blocks of memory starting at address 0. Yes, it's, oh, that's just deciding whether or not we're process ID 0 or 1 to say whether our data marker is a 0 or 1. And then we request memory from the allocator, so pling is kind of writing to the channel to say we want memory for our ID, that's our ID there, and we want 2 units of memory, this amount here, okay, and then we wait till we get our start address, and if it's this error value here, then we skip back to the start because there's no free memory available, but if there is some memory, then we check to make sure that our memory is empty, okay, and if there is some process-owned data in our memory, then we've got some kind of leak, and we set these Boolean variables here to true. So this is the dynamic checking to see whether there is some kind of information leakage between processors. Otherwise, we reset the chunk, so we say we're going to put our own data into the memory, and then at some point later, we return the memory back to the allocator. We've abstracted away all the interesting application-specific logic, and we're just presenting here the interactions with the allocator and the reallocator, and everything else is kind of thrown away.
Sorry, Jerry.
Hello.
Maybe I'm misunderstanding.
Go.
It
Yeah.
seems like a well-behaved client, right?
Ah, yes.
Thank
Thank
you.
you.
Sort of do random stuff.
Okay, so this is a well-behaved client here, I think. Yeah, good. Thanks, Brajesh. And what we're going to see is that this is a well-behaved client, but a misbehaving allocator. So the client is doing the checks because the client has certain expectations on the behavior of the allocator, and the allocator isn't correct. So the model checker will show us this in a minute. Yeah. Whereas you were expecting a well-behaved allocator and a misbehaving client, perhaps.
Perhaps, yeah.
Ah,
I was
okay.
kind of expecting to see a user that was just
Yeah, doing dodgy stuff. Okay. No, here we're looking to see is the allocator's doing the right thing or not. But, okay, thank you. That's a good clarification. Okay, here's the initialization. So we start at address 0, and we have, you know, the full length of memory to work with, and we reset our who buffer to say no data is in there, and we set our free space to say everything is free. Okay, and then we run the for processes, the allocator that's going to wait for client malloc calls, the reallocator is going to wait for free calls, and we run our 2 users that are requesting memory from the allocator. And we say our property is there is no memory leak, and that just says, you know, open memory is false. Now let me get this right. It is never the case that we eventually reach a state where there is a memory leak. So that means this variable should never be set to true, which means if it is set to true, then somehow process 0 is able to access memory that belongs to process 1. And so there's some kind of leakage of information between the 2 processes. Okay, so all I did for this was brew install spin on my MacBook. Maybe you need to apt install spin or something like that. And then I fetched my model, which is neatly written in this promula file here. Let me just get that now. Okay, less malloc 0.pml. So this is the full promula file here, which specifies all the properties and the process specifications. I kind of presented a sort of abbreviated version in the slides. And then if we say spin search, and then we're looking for a particular property, and then we see that the assertion is violated, which means we do get to some kind of state where data leaks from one process to another, and then we can go and have a look to see where that data leaked and why it leaked, and we have this kind of trace of the behavior. And eventually, what we see is that somehow in the interleaving of states between the different processes, what happens is that the reallocator or the garbage collector frees space, but then it wasn't previously an atomic block, so it freed the space, and then somebody else could come along and claim the space, but we hadn't yet reset the chunk to null out the data that was in that space. So now we've made this atomic, these 2 buffers are updated in lockstep, and so the data will be nulled out before anybody else is able to access it. So this is a badly behaving allocator that gives away memory that hasn't been zeroed out, so you can kind of leak memory from one process to another when you recycle memory. I've nearly finished. In fact, this is my last slide. So I want to conclude here. I'm thinking about 2 parts of the talk. The first part of the talk is about hardware and CHERI. I want to claim that CHERI gives us fine-grained memory protection, the granularity of individual pointers, to allow us to do this extra kind of runtime security. And then for the second part of the talk, I want to claim it's feasible to synthesize CHERI-specific allocators and then to check them, to formally verify them if we have, you know, tight property specifications, possibly using model checking technology, like I demonstrated, albeit briefly. And your homework, dear audience, is to talk to me this week, to put me straight, so I can learn from you about model checking and tagged Lisp machines and everything else that I need to know more about. I think we've got 2 minutes left for questions. Any questions?
7 minutes.
Oh, really? Oh, even better. 7 minutes left for questions. Good. Okay. Yes.
Can you summarise how, if you were taking legacy programs and recompiling them for CHERI, broadly, how much work is there?
So if we want to take legacy programs and recompile them for CHERI, it depends on the genre of the program, if you like. So if it's just a kind of you know, high-level application, you don't actually need to make, a high-level application written in kind of sensible C or C++, you don't have to do anything at all. If it's a grungy program that does horrible things to memory, then you might have to do an awful lot of changes. So one thing which nobody ever does this, but you always read about in textbooks is, you know how you can superimpose 2 pointers on top of each other by XORing them? So you can XOR 2 pointers on top of each other, and then you can have a doubly linked list with only 1 pointer cell for the forwards and backwards links in your doubly linked list. Knut talks about this in his art of computer programming. XORing pointers together is not a good idea, and it is undefined behavior in C. It works very nicely for most compilers, but not for CHERI. So you have to change that code, for instance. But basically, if you're doing anything that involves complex pointer arithmetic or casting between ints and pointers, then you need to do some re-engineering to make it CHERI compatible.
If it was reasonably same code.
If it's reasonably same C code, you just recompile it, and there's no change necessary. So I think the folks from Cambridge have this amazing figure. They say you need to change 0.02% lines of your code, which is like 1 in every 10,000, no, 2 in every 10,000 lines of code, something like that. You need changing. We found for our memory allocators is much higher because, of course, memory allocators are doing grungy things with kind of addresses and so on. But even there, it was still less than 2% of your lines of code. So yeah, re-engineering or refactoring for CHERI is certainly feasible. Yeah, okay. And sorry, I'll come to you in a minute. Sorry, just another thing to say is we've been refactoring in Glasgow a conservative garbage collector, the Bohm garbage collector, which is used so you can do garbage collection in your C code rather than manual memory management. And it's a well-used open source garbage collector, and we refactored it for CHERI, and now other people who have other tagged memory architectures are using our port and just changing the macros to run with their tagged architecture. So you fix something for CHERI and fix it to any tagged architecture. Yeah, thanks. Hello.
You said that 2 in 10,000 need to be changed.
Oh right, this is good. The needle in the haystack problem. How to know which 2 in 10,000 lines you need to change? That's a really good question. Thank you. Good. Okay, so there are some tools that will help you with that. So the compiler itself is actually very good and helps you. I wonder if I could demonstrate that here. Let me see. Oh, I might have just crashed Zoom. Have I? Let me see. But we're finished anyway, so it doesn't really matter too much if we've crashed Zoom now. Help. What I really wanted to do was go to here and see if I could. This is actually a real CHERI machine here in Glasgow. So I've turned on my VPN and I've logged into a real CHERI machine. And here I think I've got my bounds.c program. Let's see if we find that bounds.c. Yes, okay. And in here, if I compile this for Morello and turn on all my warnings, no, maybe this won't work actually. Sometimes when you recompile it for Morello, it will automatically tell you, because it checks whether you're kind of doing something that looks a bit dodgy. This might not. Let's see. Enjoy. It doesn't. Okay, I've got a better example somewhere that does. But sometimes you can statically show that, you found one of those 2 in 10,000 lines of code that are dodgy. There are also some other kind of static analysis tools that will help you to pinpoint the dodgy lines of code, because you know what they're going to look like. They're going to be things that are manipulating pointers in ways that probably aren't legal C, or if they are, don't respect bounds in the way that CHERI needs them to. So yeah, you can get help finding the lines of code. So I've got this is a kind of lecture trick. But when you get a brilliant idea, you say, I just need a final year undergraduate student to implement this project for me. So this is my brilliant project idea for this year. So final year project students are just kind of limbering up in Glasgow. They'll be starting in September, we'll be looking at the project. So my project idea is, right, why don't we train some kind of machine learning synthesis tool, and we say, here's the code before we ported it to CHERI, and here's the code after we ported it to CHERI, here's the diff, right, okay, And that's the kind of changes you need to make to cherify your code. And then we'll give it, you know, an operating system kernel it's never seen before, and it will magically make it work for CHERI. So that's my project idea, suggestion for my new level 4 project students this year. So we'll see if any of them are foolhardy enough to take up that project. But I think, you know, with appropriate training data, a nice corpus of C code, you can possibly automatically identify the places where you might need to fix up your code for CHERI. What do CHERI fixes look like? That's an interesting question as well, isn't it? So often it's being more careful with your casting and using perhaps intermediary variables and making sure that you don't kind of lose capability metadata. So that code I sent you to before, let me see if we can find it again, the capabilities for coders page, that website there, has lots of advice about, let me see if I can find some advice here. So here's some code that and 2 pointers together, which isn't a good thing to do in CHERI. So in CHERI, instead, you should change the type of one of your pointers and change the type of your other pointer to something different, and then it all works fine. So there are kind of small fixes, kind of well-known rewrites that you can do to make your code CHERI compatible. Thank you for your question. Hello.
So for CHERI, in reality, very much percentage of researchers they can access real CHERI computers.
Yeah, how do you access real CHERI computers? So as I say, the UK government had this research program, and they persuaded ARM to build 1,000 machines. There might still be some left. I don't know. There was certainly a small number left last time I looked. So on the capabilities for coders site, question 2 is, how do I get a Morello board? How do I get my own capability hardware? And the answer is, fill in this online form. So it might be worth trying to do that, perhaps, to fill in a form. And somebody from the Innovate UK organisation will get in touch with you and say, do you want a Morello board? We can give you one if you like. So you could try and get access to the hardware. It's also the case that there are these FPGA models now, so you can run something on an FPGA, and that might be one workaround. Yeah. Alternatively, talk to somebody nicely who's got a board, and they might give you a remote login to it, perhaps. We've certainly done that with Glasgow for people that we know who are nearby in Scotland. So, yeah, if you know somebody local who's got a Morello board, they're almost kind of obliged to share it with other researchers. So you might be able to. Yeah, but as I pointed out, you can do everything you want with software simulation. It's just very slow. But it is possible to do it all. So, for instance, if you go to this site here, CHERI.run, and wait for a long time, there we go. You can run it in a Docker, and you can get the emulated layer there, perhaps. Yeah. Last question, and then I think it's probably time to stop. Last question. Speak now or forever hold your peace.
I can continue talking to Jeremy.
Yeah. Thanks.